Today on How It's Made. Tasers. Canned soup. Jaw harps and mouth bows. And diving boards. A taser device fires bursts of electricity to deliver a high-voltage, low-amp shock that temporarily disables the subject. Invented in 1969 by an American aerospace scientist, the taser has become a weapon of choice for police forces around the world. Today, when an officer reaches for his or her gun, it's often one without bullets. From a cartridge on the front, the taser fires electrified darts, which on impact cause muscle contractions in the target subject. The subject is immobilized but usually recovers in a few minutes. This metal capsule contains the propellant, pressurized gas. A robotic arm inserts the capsule in a plastic chamber. The next robot places a part called the primer disc on the capsule. It contains chemicals to generate a mini explosion that will drive pins into the capsule, releasing the gas. Another robot adds a protective screen. That's the primer disc on the left and the screen on the right. They punch out a round piece of foam, and the robot thrusts it into the chamber and tamps it down. After welding it in place with ultrasonic vibrations, a robot flips the unit up and into a second plastic chamber. The placement leaves just enough space between the inner and outer chambers for wire bundles to be inserted later. A robot then tucks the assembly into the plastic cartridge. It has slots for other components like insulated copper wire bundles. A machine winds the wire in a tight figure-8 formation. This wire will electrify the darts as they're deployed, and the figure-8 winding reduces the possibility of tangling. A worker places two bundles in the designated spaces in the cartridge. He tops each bundle with a piece of strong polyester film. It keeps the wire pack from springing apart as he slides it off the fork and presses it into the cartridge. He's now ready for the barbed taser darts. He threads the end of each wire bundle through one and knots it. He installs the darts in the cartridge, using a special tool to seat them correctly. He selects plastic wedges, one for each wire, and wraps the other end of the wires around it. He attaches electrodes to facilitate the flow of electricity to the cartridge. The next part is called the blast door. It will blast apart and break in two as the taser darts are deployed. The robot snaps it in place on top of the cartridge. The door is color-coded to signify the range of the dart probes. Yellow indicates 5 yards. With the compressed air cartridge complete, they now focus on the taser's deployment mechanisms. A technician installs a laser system and 2 LED lights in the plastic casing. The laser is an aid for aiming the electrified darts, and the lights will illuminate the target. He adjusts the laser's aim to sync it with one of the darts, using a bullseye target as an alignment aid. Next, they immerse the high-voltage board in epoxy resin and pump more directly into it. This board is in the part of the taser gun that generates electrical pulses when the gun is in stun mode. Once cured, the epoxy encapsulates this unit to insulate the components. The technician inserts the high-voltage board in the gun casing, along with the controller board, the brains of the taser. He also installs an information display board and makes the necessary connections. He plugs the assembly into a power source and tests the laser and LED lights. He snaps on the trigger and confirms that it makes contact with the plunger on the control board. He joins the other half of the taser casing to the one with all the working parts. Then an ultrasonic welder fuses the casing parts at the tongue and groove seams. Protecting the outer casing with the sheet of plastic, the technician welds a safety switch to the trigger. This critical part will prevent accidental deployment. In a test chamber now, they activate the taser without the air cartridge. Without the cartridge and its projectile darts, the taser works as a handheld stun gun to zap the target directly. Once it meets the tester's approval, this taser is ready for the police beat. A consumer model is also approved for use in some jurisdictions. Like the police version, it should deliver a shocking performance. Soup is a liquid food that is as old as cooking itself. Its appeal is quite literally biblical because in the Old Testament, a son trades his inheritance for a pot of lentil soup. Of course, today, one doesn't have to sacrifice it all for soup because it's usually readily available in cans. With the invention of canning in the early 19th century, soup soon became available on demand. On the home front, this caused quite a stir. No need for a long simmer. Just open the can, reheat, and soup's on. To manufacture lentil soup, they make a hearty soup base. They load measured amounts into a heated mixer, beginning with pureed garlic. The mixer's walls are steam jacketed so the mix will cook evenly, with no scorching on the bottom. The next ingredient is olive oil. They activate the steam heat, and the garlic begins to sizzle. They add chopped onion. The mixing blades gently toss the ingredients as they sauté. They blend in diced celery and cook until translucent. The next round of ingredients takes the flavor up a notch. They include chopped carrots, sea salt, and fragrant spices. Balsamic vinegar adds a sweet tartness to this lentil soup base. They're now ready to liquefy the ingredients. They open the tap and filtered water spills in. As the soup begins to simmer, they add crushed and diced tomatoes. The final ingredient for this robust lentil soup base is spinach. Mixing it makes for a colorful swirl, and as the ingredients cook, they become increasingly aromatic. Meanwhile, raw peeled potatoes ride a steep and slatted conveyor upward. The slats keep the potatoes from rolling back as they make the climb up to a hopper. From the hopper, the potatoes slide down a chute and into a revolving drum with cross-cutting blades. The blades cut the spuds into small cubes and spit them out. After a trip past a metal detector, the potato cubes land in a bin. In small cube form, they'll cook faster later. Next, lentils, hard and dried, surge in a steady stream onto a revolving round table. The table has openings that lead to little chutes with doors. They open to funnel the lentils into cans moving on a conveyor below. This ensures that a specific amount is fed into the cans. Partially cooked green beans and the raw potato cubes now flow onto a second revolving table. The cans with the lentils have now moved into position below. The veggies fall through the holes and into the cans. The cans with mostly uncooked ingredients now head towards the piston filler. It pipes the steaming hot vegetable soup base directly from the kettle mixer into the cans, filling them to the brim. Immersed in the hot liquid, the lentils, potatoes, and green beans at the base of the can cook a little and soften up. Sensors detect the approach of the cans and cue the lids. The lids drop one by one onto the cans below. A device then interlocks the rims of the cans and the lids for a hermetic seal. The cans move into another lane and travel past an X-ray machine. It scans the soup inside for metal contaminants like stray bolts or screws. If the images are clear, the cans of soup move on to a giant pressure cooker. Here, the contents cook under pressure for about a half hour. Pressure cooking simulates the effect of a long simmer in a fraction of the time. The soup then cools for 10 minutes. It is now thoroughly cooked and preserved. Now on their sides with glue applied, the cans of lentil soup roll over labels and the labels adhere. They produce more than 15,000 cans of lentil soup an hour at this factory. That's 105,000 cans in one shift. It's enough to feed a small city. The jaw harp and the mouth bow are among the earliest musical instruments. A Chinese drawing from the 4th century BC is believed to be the first record of a musician playing a jaw harp, and cave paintings in southern France from 15,000 BC depict someone playing a mouth bow. The mouth bow is a stick of wood with a single string the musician plucks or strums, while altering the vibration-generated sound by mouth. The jaw harp is a metal instrument. The musician plucks its flexible tongue to produce a twanging sound, which he then modulates with mouth positions and breathing. This craftsman makes the jaw harp's frame out of a 1/10 of an inch thick square steel rod. He measures and marks the required length and bend points. He cuts the length with the standard hacksaw, clamps the rod in a vise, then slips metal pipes over the ends to prevent them from twisting, as he bends them to form the arms of the frame. He aligns the arms, leaving just enough space between them to allow the tongue to vibrate without obstruction. For the instrument to produce quality sound, the arms must be perfectly parallel to each other, their edges in mirror image. He marks the tongue's position in between the arms and files down the metal within the markings. This creates a notch in which the tongue will sit. The tongue is made of spring steel, a type of steel which, when bent, resumes its original shape. Before attaching it, he saws a tiny undercut in each side of the notch. Then he inserts the tongue and hammers the undercut sides to compress them over the tongue and lock it into position. He heats the tip of the tongue with a propane torch. Once the metal softens enough to bend, he angles the tip to form what's called the trigger. Then he heats the end of the trigger and bends it into a loop. This is what the musician's finger strikes to make the tongue vibrate. Finally, he files the tongue's edges sharp, a last detail to improve the instrument's sound quality. To make a mouth bow, his first step is to find a stick that's between roughly 1.5 to 6.5 feet long, not too heavy, and ideally with a T-shape at the end. In his workshop, he clamps it in a vise, trims it to the required length, and using a rasp, files the knots flat. He files the top end until it's about 2/10 of an inch thick. This forms the mouthpiece, which you hold gently to your lips while plucking the string. The string vibrates the mouthpiece, producing sounds that you alter by changing the shape of your mouth. He drills a hole toward the base of the mouthpiece for the string. Then, just below that, files a notch for the bridge that supports the string. Just below the notch, he hammers in a steel nail, called the pin. He drills a 2/10 of an inch hole at the T-shaped end of the stick. This is where he'll insert the tuning peg, which he constructs out of a wood knob and dowel. He makes the string from a length of piano wire. He forms a loop at one end by twisting it with pliers around an awl. He feeds this end through the hole at the base of the mouthpiece and hooks the loop onto the pin. Then he threads the other end of the string through a hole in the shaft at the tuning peg at the bottom of the stick. He turns the peg to tighten the string. Just as on a violin or guitar, the tauter the string, the higher the note it produces. The final step is to position the bridge, a hardwood dowel, in its notch under the 10th string. By elevating the top of the string, the bridge prevents it from cutting into the stick. The mouth bow and the jaw harp are played alone or alongside other instruments in the folk music of numerous cultures around the world. The earliest known reference to a diving board appears in a hieroglyphic from 480 BC. It depicts a man plunging headfirst into a pool of water from a platform. Today, diving boards are standard equipment at neighborhood and backyard swimming pools. One end of the diving board is fixed to give the other end the bounce required for a big splash cannonball or a graceful swan dive. To make the diving board shell, workers load a sheet of acrylic into a clamping machine that transports it into an oven. The oven heats the sheet for about 30 seconds to soften it. Then a forming machine applies suction to draw the softened acrylic tightly over a mold in the shape of two diving boards. Fans blow cool air, hardening the acrylic to this shape within seconds. They extract the molded acrylic, then saw it in half to separate the two diving board shells. They coat the shell surface in a resin and fiberglass mixture. This tool is called a chopper gun because it chops and shreds the fiberglass string, then shoots it out drenched in resin. They roll it to compress the fibers and push out air pockets. Any trapped air would create a weak spot in the diving board. After letting the resin dry and harden for 30 minutes, they begin filling the shell cavity with 2/10 of an inch thick fiberglass mat. They drench the mat in resin, rolling it over to ensure every fraction of an inch gets well saturated. Then they lay down another fiberglass mat, this one a bit thinner, and saturate it with the existing resin. The diving board's core is made of laminated wood, which is several thin layers of wood glued together. Laminated wood is actually stronger than a solid piece of wood. After rounding the top edge, they lay 2 wood laminate cores over the resin-saturated fiberglass mats. They position clamps to hold the cores in place. But before tightening, they insert metal spacers to ensure the cores are correctly positioned within the shell. Once the positioning is perfect, they tighten the clamps, then let the resin cure at room temperature for a half hour or so. Then the clamps come off, and workers cover the cores with an even thicker fiberglass mat impregnated with resin. This is the bottom of the diving board. They make sure the mat is centered. Then manually form it to the shape of the board, pushing out the air pockets as they go. They spray on some decorative paint, then put the board in an oven for 24 hours to cure. When it comes out, they use a diamond blade to saw off the excess fiberglass around the edge. Then they do a final trimming to make the edge neat and smooth. They mask the sides with tape, leaving only the top exposed. This is where they'll now apply a rough texture, a safe, non-slip surface. First, they roll on a thin coat of resin. Onto that, they sprinkle a layer of silica sand, making sure to cover the surface thoroughly and evenly. The sand sticks to the resin, which sets and cures in about 15 minutes. After sweeping off the excess sand that didn't adhere, they roll on a coat of laminating resin, which bonds to the sand, giving the surface a clean, finished look. They pull off the tape and apply the manufacturer's decal to the side. The diving board is now all set to be installed on a stand at the edge of the deep end to await anyone ready to take the plunge.